It's very far above my expectation.
Show the customers what we can do with our product.
This machine here is the newest addition to our arsenal of equipment at Siggy, and this is called an Air Classifier, and its purpose is to fractionate flours into their main component. So what I can do is I can take this flour, put it through the system, and separate a coarse fraction and a fine fraction. The coarse fraction will be the starch, and then the fine fraction will be the protein. The flour that goes in here must be very finely milled, usually impact milled or pin milled, to get a particle size a little bit smaller than your regular white flour would be. The particle size would be between 20-30 microns all the way up to maybe 80 or 100 microns. Whereas regular flour is a little bit above 100 microns. The separation is made based on volume and density of the particles. Starch tends to be larger particles, proteins are smaller particles. The purpose of all this is that there is an emerging market of fractions from flours, and fractions from flours have unique functional characteristics as opposed to a regular flour. So some of the things that we can do with fractions from flours, for instance, the starch fraction can be used in products like pasta, baked products, batters and coatings, extruded snacks, fillings, and salad dressings. Whereas the P fraction, which is the fine fraction, could be used to increase protein in food products, or even used in beverages, things like granola bars, baby foods, pastas. It's very popular in meat products, veggie burgers, or other baked goods. So the way it works, basically two principles. One is centrifugal force, and the other one is friction. And the friction force is supplied by the movement of air. The centrifugal force is supplied by a spinning disc inside this section here. So I take my flour, in this case we have split yellow pea flour. It is fed through by a rotating screw, and it's introduced into this chamber here. There is a rotating wheel. It's called the classifier wheel inside here, and as well as airflow. So the particles get separated in here. The coarse fraction comes through here, which would be the starch fraction. The fine fraction keeps on going and is deposited in this container here, and this would be the protein fraction. Each pulse flour is different. We can have chickpea flour, or lentil flour, or bean flour, and the parameters have to be set differently. So we may have to set the air flow differently, or the speed of the wheel differently, to get the desired particle size cut point that we wanted. Once the product is finished running through, what I want to do is I want to see how efficient the process was. So ideally I would like to have a really concentrated protein fraction, and that to me will mean that the process was efficient and the settings were set correctly for that particular flour. So what I will do is I'll take the fine fraction and I'll do a protein analysis on it, and that will tell me how much protein I have in it. So what I would expect in this process is that I would start off with about 20 to 25% protein in the regular flour, or the starch flour, and then the fraction would be around 60% protein, so more than double what I've had before. And at that point, this product has unique functional characteristics versus this product, or any other flour for that matter, because of the high protein. So this is the protein fraction, most likely around 55 to 60% protein, and this would be the coarse starch fraction. So far to date at Siggy, we've done work with yellow pea flour, and we're learning how it reacts when put into the system. And we also have done work with lentil flour as well. We'll be doing many more projects with different pulses, and even looking at different pre-treatments prior to this process to see how efficient the process can be. So this is a lab scale model, and these pieces of equipment on a commercial scale are very large. So before we do any work on a commercial scale, we need to know how these products behave on a small scale.